On a clear night, far away from city lights, look up. The sky appears overflowing with stars. Thousands of tiny points of light stretch from one horizon to the other, forming a glowing river across the darkness. To our eyes, the universe feels crowded, alive with suns, planets, galaxies, and endless celestial wonders. For thousands of years, that impression shaped the way humanity imagined the cosmos. We believed the universe was filled with things. Filled with stars, filled with galaxies, filled with light. But the deeper science has explored the universe, the stranger the truth has become. Because everything you can see tonight is almost nothing. Not a small part, not a tiny fraction. Almost nothing. The greatest surprise in modern cosmology is not how much exists. It is how astonishingly little exists. The universe is dominated not by stars, not by planets, not by galaxies, but by emptiness. Imagine removing every galaxy, every star, every planet, every asteroid, every atom of dust floating between the stars. What would remain? Almost exactly what exists already. An unimaginable ocean of empty space. According to the thought experiment explored in this documentary, all of the visible matter in the observable universe occupies only about 7.8 times 10 minus 8% of its total volume. Whether expressed as a mathematical illustration or visual analogy, the conclusion remains deeply unsettling. Matter is almost insignificant compared with the enormous emptiness surrounding it. To understand just how extreme this idea is, let us shrink the observable universe down to the size of Earth. Picture our planet floating silently in space. Its oceans, mountains, deserts, and continents now represent the entire observable universe. Every galaxy ever photographed, every star that has ever burned, every planet that has ever formed, every black hole, every nebula, every human being, everything made from ordinary matter. Compress all of it together. The result would occupy a volume smaller than a single proton. One of the smallest particles inside the nucleus of an atom. The comparison sounds impossible. Yet, mathematics consistently points toward the same astonishing conclusion. The universe is not a crowded place. It is almost perfectly empty. And that immediately raises a profound question. If the universe is so empty, why does it appear so full? The answer begins with the limitations of human perception. Our eyes evolved on Earth, a planet surrounded by dense air, oceans, forests, mountains, and life. Everything in our daily experience exists at relatively high density. Walk through a city, and every direction contains buildings, people, vehicles, trees, and signs. Even standing in the middle of an opened desert, countless billions of air molecules still surround your body. To us, empty usually means an abandoned room or a quiet stretch of highway. The universe operates on a completely different scale. The average distance between neighboring stars is measured not in miles or kilometers, but in light years. Light itself, traveling at nearly 300,000 kilometers every second, requires more than 4 years to reach the nearest star beyond our sun. Between those stars lies almost nothing. The same pattern repeats at larger scales. Galaxies contain hundreds of billions of stars. Yet galaxies themselves are separated by millions of light years. Between them stretches an even greater emptiness. Expand farther still, and galaxies form clusters. Clusters form superclusters. Superclusters connect into enormous filaments known as the cosmic web, and between those filaments, Vast cosmic voids dominate the universe. Wherever we look, emptiness wins. Even this realization does not go far enough, because the emptiness does not begin between galaxies. It begins much closer to home. Look at your own body. It feels solid. Your hands seem substantial. Your bones feel rigid. The chair supporting your weight appears completely full. Yet every atom inside your body is itself almost entirely empty space. If the nucleus of a hydrogen atom were enlarged until it became the size of a marble sitting in the center of a football stadium, the electron would orbit somewhere near the outer seats. Everything between them would be almost entirely empty. The solid world exists not because matter fills space, but because quantum forces prevent atoms from passing through one another. In other words, even you are mostly empty space. The universe follows the same pattern at every scale. Atoms are mostly empty. Solar systems are mostly empty. Galaxies are mostly empty. The observable universe is overwhelmingly empty. Nature seems to repeat the same design over and over again. This repetition forces us to confront an uncomfortable possibility. Perhaps emptiness is not the exception. Perhaps emptiness is the rule. That idea challenges one of our deepest intuitions. When we imagine creation, we tend to focus on objects, stars, planets, nebulae, black holes. But modern cosmology suggests that the true story of the universe may be written not by the things that exist, but by the vast spaces separating them. The silence between the notes creates the music. The blank spaces give meaning to the words on a page. Likewise, the enormous voids between galaxies define the architecture of the cosmos itself. Without them, the universe would be unrecognizable. At first glance, this emptiness feels wasteful. Why would a universe capable of producing hundreds of billions of galaxies leave almost all of its volume completely vacant? Why not fill space with more stars, more planets, more matter? The answer may be one of the most surprising discoveries in modern physics. The universe is not empty because something failed to form there. It may be empty because it has to be. If matter had been packed even slightly more densely after the Big Bang, gravity would have overwhelmed the young universe. Stars would have formed too rapidly. Galaxies would have collided more violently. Countless regions might have collapsed directly into black holes before stable planetary systems ever had a chance to emerge. On the other hand, if matter had been distributed only slightly more thinly, gravity would have struggled to gather gas into stars at all. Galaxies might never have formed. The heavy elements needed for planets and for life would never have been forged inside stellar cores. The universe would have remained a cold, nearly featureless sea of hydrogen and darkness. Somehow, the cosmos exists in an extraordinarily narrow balance, dense enough for gravity to build magnificent structures, sparse enough to prevent those structures from destroying one another. That balance is so delicate that cosmologists continue debating whether it arose inevitably from the laws of physics or reflects something even deeper about the universe itself. This question becomes even more remarkable when we examine the earliest moments after the Big Bang. Tiny quantum fluctuations, differences in density no greater than about 1 part in 100,000, would eventually grow into every galaxy, every star, every planet, and every living organism that has ever existed. Everything we know began as almost unimaginably small imperfections inside an almost perfectly uniform universe. The emptiness was not accidental. It was part of the blueprint from the beginning. But the story does not end there. The universe is not becoming less empty. It is becoming more empty. At this very moment, space itself is expanding. Galaxies are drifting farther apart. Immense cosmic voids continue growing larger. The invisible influence known as dark energy is accelerating that expansion, slowly increasing the distances, separating nearly every galaxy in the observable universe. In the unimaginably distant future, civilizations living billions or even trillions of years from now may look into the night sky and see almost nothing at all. Most galaxies will have disappeared beyond the cosmic horizon. The universe will seem far smaller than it truly is. Not because the cosmos has shrunk, but because emptiness has continued to grow. This realization changes the way we think about our place in existence. We often imagine humanity as isolated because we have not yet found other intelligent civilizations. Perhaps the greater truth is even more profound. The universe itself is built upon isolation. Everything is separated by extraordinary distances. Stars, galaxies, galaxy clusters, even atoms. Nature seems to favor space over substance, silence over noise, distance over closeness. And yet, paradoxically, that immense emptiness is precisely what allows complexity to exist. Without the vast spaces between stars, planetary systems could not remain stable. Without the enormous distances between galaxies, the large-scale structure of the universe would collapse into chaos. Without empty space inside atoms, chemistry itself would be impossible. The void is not the absence of creation. It is the condition that makes creation possible, and that leads us to the central question of this journey. If emptiness is so fundamental, if it exists from the quantum world to the largest structures in the observable universe, if it has shaped the formation of every galaxy, every star, every planet, and every living being, then why does the universe insist on being so astonishingly empty? Is this merely an accident of cosmic history? Or is the terrifying emptiness surrounding us the inevitable consequence of the deepest laws governing reality itself? To answer that question, we must begin where every structure in the universe was first born. In the earliest moments after the Big Bang, when the blueprint of cosmic emptiness was written into the fabric of space itself. When we hear the word vacuum, most of us imagine absolute nothingness. No air, no light, no sound, no matter, simply nothing. It seems like the simplest concept imaginable. A completely empty space. Yet modern physics tells us something astonishing. True emptiness may not exist at all. The universe appears empty because our senses cannot perceive what is actually happening within its vast expanses. In reality, even the darkest regions between galaxies are far stranger than silence alone. To understand why the universe is almost entirely empty, we must first answer a surprisingly difficult question. What is empty space? Centuries ago, philosophers argued fiercely over whether a perfect vacuum could even exist. Aristotle famously declared that nature abhors a vacuum. He believed empty space was impossible. Everything, he argued, had to be filled with something. For nearly 2,000 years, that idea remained influential. Then, science began to challenge it. Experiments during the 17th century demonstrated that air could indeed be removed from a sealed container. Vacuum pumps created spaces where almost no matter remained. It seemed that humanity had finally discovered true emptiness. But the deeper physicists looked, the less empty the vacuum became. Classical physics viewed space as an enormous stage upon which the universe performed. Stars moved through it. Planets orbited within it. Light traveled across it. But space itself remained passive. It simply existed. Albert Einstein transformed that picture forever. According to general relativity, space is not merely an empty container. It possesses geometry. It stretches. It bends. It expands. Gravity itself is nothing more than the curvature of space-time. Even before introducing quantum mechanics, empty space had already become an active participant in the evolution of the universe. Then quantum physics arrived and made the vacuum even stranger. In quantum mechanics, the vacuum is not a place where nothing happens. Instead, it represents the lowest possible energy state of reality. That distinction changes everything. Imagine the calm surface of a lake. From a distance, it appears perfectly still. Approach more closely, and tiny ripples become visible. Look closer still, and microscopic vibrations constantly disturb the surface. The quantum vacuum behaves similarly. Even when every particle has been removed, activity remains. Tiny fluctuations continuously ripple through space itself. These fluctuations arise from one of the most fundamental principles in quantum mechanics, the Heisenberg uncertainty principle. Contrary to everyday intuition, nature does not permit every physical quantity to possess perfectly definite values simultaneously. Energy, like position and momentum, is subject to quantum uncertainty. As a consequence, the vacuum can briefly borrow tiny amounts of energy. This borrowed energy allows particle-antiparticle pairs to appear spontaneously. They exist for extraordinarily short intervals before annihilating one another and returning their energy to the vacuum. This process happens everywhere, every second, across the entire universe. The emptiest regions of intergalactic space are therefore filled with invisible quantum activity. Physicists call this remarkable environment the quantum vacuum. Although these virtual particles cannot normally be observed directly, their effects have been measured experimentally. One famous example is the Casimir effect. Place two perfectly conducting metal plates extremely close together inside a vacuum. Quantum fluctuations between the plates become slightly restricted compared with those outside. The result is a tiny but measurable force pushing the plates together. Nothing touches them. No air exists between them. Yet quantum fluctuations generate a real physical effect. The vacuum is alive. Far from being empty, it constantly seethes with microscopic activity. This realization transforms the meaning of cosmic emptiness. When astronomers describe the enormous voids between galaxies as empty, they do not mean absolutely nothing exists there. Instead, they mean almost no ordinary matter occupies those regions. The distinction is subtle, but profoundly important. Now let us expand our perspective. Imagine leaving Earth aboard a spacecraft. Within hours, you pass beyond the Moon. After several months, you cross the orbit of Mars. Years later, you leave the solar system entirely. Ahead lies the nearest star, Proxima Centauri. It appears close on astronomical maps. In reality, it is approximately 24 light-years away. Traveling aboard today's fastest spacecraft would require tens of thousands of years to reach it. Everything between our Sun and Proxima Centauri consists almost entirely of empty space. Occasional atoms drift through the interstellar medium. Tiny dust grains wander silently between the stars. But compared with the immense volume separating them, matter is astonishingly scarce. The same pattern repeats again. Our Milky Way contains roughly 100 to 400 billion stars. At first glance, that number sounds unimaginably crowded. It is not. If every star were represented by a grain of sand, the average separation between neighboring grains would still be enormous. The galaxy itself is mostly empty. Now zoom outward. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away. Between the Milky Way and Andromeda stretches another immense ocean of nearly empty space. The local group of galaxies occupies only a tiny fraction of its surrounding volume. Expand farther still. Clusters of galaxies appear, then superclusters. Finally, vast filaments spanning hundreds of millions of light-years connect across the observable universe. Between these filaments lie gigantic cosmic voids. Some extend for more than 300 million light-years. If our galaxy vanished tomorrow, one of these immense voids would scarcely notice the difference. Matter occupies only the thin threads. Emptiness fills everything else. Remarkably, this pattern is not unique to astronomy. Nature repeats it at every observable scale. Let us return to the atom. Imagine enlarging a hydrogen atom until its nucleus becomes the size of a basketball placed at the center of a sports arena. Where would the electron be? Not beside the nucleus, not even inside the basketball court. It would occupy a region roughly the size of the entire stadium. Everything between the nucleus and the electron consists almost entirely of empty space. If every atom inside your body lost that empty space while keeping only its nuclei and electrons compressed together, your entire body would shrink to a volume far smaller than a grain of sand. You would weigh exactly the same. Only the emptiness would disappear. The apparent solidity of matter does not arise because atoms are packed tightly together. Instead, it emerges from electromagnetic forces governed by quantum mechanics. Electrons surrounding neighboring atoms repel one another. That repulsion prevents your hand from passing through a table. Matter feels solid because quantum fields resist overlap. Not because atoms are physically full. In an extraordinary sense, every object you have ever touched is mostly empty. The chair beneath you, the walls around you, the mountains, the oceans, your own body. The universe repeats one elegant design from the smallest scales to the largest. Empty space dominates. Matter merely decorates it. This realization changes our understanding of creation itself. We often think of the universe as being built from matter. Perhaps it is more accurate to say that matter is suspended within an immense framework of emptiness. The void is not the exception. It is the foundation. But why should nature organize itself this way? Why not produce a universe packed densely with stars and galaxies? The answer lies partly in gravity. Gravity weakens rapidly with distance. As matter spread outward following the Big Bang, only tiny density variations gradually attracted enough material to form galaxies. Most regions never accumulated sufficient matter to create stars. Instead, they remained empty. Over billions of years, gravity amplified this contrast. Dense regions became denser. sparse regions became emptier. The universe naturally separated itself into islands of matter surrounded by expanding oceans of space. This process continues today. As galaxies cluster together, the surrounding voids grow even larger. Dark energy accelerates that expansion, making the emptiest places in the universe steadily emptier. The cosmos is not evolving toward greater uniformity. It is becoming increasingly divided. Rich regions gather more matter. Poor regions lose what little they once possessed. The emptiness expands. Yet there is another remarkable consequence. Precisely because space is so empty, light can travel extraordinary distances. The photons entering your eyes tonight may have crossed millions, or even billions, of light years without colliding with anything substantial. If the universe were only slightly denser, much of that light would scatter repeatedly before reaching us. The night sky would look completely different. The transparency of the cosmos depends directly upon its extraordinary emptiness. In a very real sense, we can study the distant universe only because there is so little inside it. The void itself has become astronomy's greatest ally. As strange as the quantum vacuum appears, as astonishing as atomic emptiness seems, and as enormous as the cosmic voids have become, they all point toward a deeper truth. The universe did not accidentally become empty. Its emptiness emerged from the same physical laws governing gravity, quantum mechanics, and cosmic expansion. It exists consistently across every known scale of nature. From the invisible fluctuations of quantum fields, to the spaces inside atoms, to the gulfs separating galaxies, one principle echoes throughout the cosmos. Reality is built far more from emptiness than from matter. And yet, paradoxically, it is precisely this immense emptiness that allows every star to shine, every planet to orbit, every atom to exist, and every living observer to ask why the universe chose such an extraordinary design. The answer may have begun long before the first galaxy ever formed. It may have been written into the universe itself during the first tiny fraction of a second, after the Big Bang, when the distribution of matter and the vast emptiness surrounding it was established for all cosmic history to follow. Every galaxy, every star, every planet, every black hole, every atom inside your body, everything that has ever existed began with a single event, the Big Bang. For nearly a century, this phrase has become one of the most recognizable ideas in science. Yet it is also one of the most misunderstood. When most people hear the words Big Bang, they imagine an enormous explosion, a gigantic fireball erupting into an empty universe, matter blasting outward in every direction, like fragments from a bomb. It is an image repeated endlessly in movies, television documentaries, and popular illustrations. It is also fundamentally wrong. The Big Bang was not an explosion in space. It was the expansion of space itself. There was no giant sphere flying through an already existing universe. There was no center from which galaxies were launched. Instead, space itself began stretching everywhere at once. Every region expanded simultaneously. Every future galaxy participated in that expansion. Imagine drawing dots across the surface of an uninflated balloon. Each dot represents a future galaxy. As the balloon inflates, every dot moves away from every other dot. None of the dots occupies the center of the expansion. The surface itself is growing. Our universe behaves in much the same way. The galaxies are not racing through empty space. because of some ancient explosion. Space itself has been expanding for nearly 13.8 billion years. This distinction changes everything, because if space itself was expanding, then the enormous emptiness filling today's universe may have been created alongside the expansion itself. But another mystery immediately appears. Why did matter not spread out perfectly evenly? Why did galaxies form at all? If the young universe had been completely smooth, gravity would have had nothing to work with. No stars, no galaxies, no planets, only an endless sea of nearly uniform gas. Yet that is not what happened. Somehow, tiny regions became ever so slightly denser than their surroundings. Those slightly denser regions attracted more matter. Gravity amplified the differences. Over billions of years, those tiny irregularities evolved into the magnificent cosmic structures we see today. Where did those irregularities come from? The answer may lie in one of the strangest ideas in quantum physics: quantum fluctuations. Even in the earliest moments after the Big Bang, the universe was not perfectly uniform. At unimaginably small scales, quantum mechanics does not allow complete stillness. Tiny fluctuations in energy constantly appear and disappear. These fluctuations are normally microscopic, almost insignificant. But during the earliest fraction of a second in cosmic history, something extraordinary happened. The universe experienced an event known as cosmic inflation. According to the inflationary model, the universe underwent an almost unimaginably rapid period of expansion. In far less than a trillionth of a trillionth of a trillionth of a second, space expanded by an enormous factor. Regions once smaller than atomic nuclei became astronomically large. The expansion happened so quickly that tiny quantum fluctuations were stretched across the entire universe. Imagine drawing tiny ripples on the surface of a balloon before inflating it. As the balloon expands, those tiny ripples become enormous patterns covering its surface. Inflation appears to have done something remarkably similar. Quantum fluctuations that originally existed on microscopic scales became the seeds from which every galaxy would eventually grow. In other words, the largest structures in the observable universe may owe their existence to quantum uncertainty. This astonishing connection links the smallest scales imaginable with the largest structures ever observed. Without quantum mechanics, there might never have been galaxies. Without inflation, those quantum fluctuations would have remained microscopic forever. Together, they produced the blueprint of the universe. But there is something even more remarkable. The blueprint was almost perfectly smooth. Not completely, just almost. When scientists studied the cosmic microwave background, the faint afterglow left behind approximately 380 zillion years after the Big Bang, they discovered something extraordinary. The temperature of the young universe was astonishingly uniform. Across billions of light years, differences measured only about 1 part in 100,000. That tiny number changed everything. Imagine looking at a perfectly smooth lake. Now raise one ripple by only 1 millimeter while leaving the surrounding water unchanged. The difference seems insignificant. Yet in the universe, similarly, tiny differences eventually produced clusters containing trillions of stars. The entire visible cosmos grew from fluctuations almost too small to imagine. This remarkable balance raises one of the deepest questions in cosmology. Why were the fluctuations exactly this size? What if they had been larger? What if they had been smaller? The answers reveal how delicately balanced our universe truly is. Suppose the density fluctuations after inflation had been significantly larger. Gravity would have gained a much stronger advantage. Dense regions would have collapsed rapidly. Gas clouds would have compressed violently. Instead of gradually forming galaxies over billions of years, enormous quantities of matter might have collapsed almost immediately into black holes. The young universe could have become a chaotic landscape dominated by gravitational collapse. Stars would rarely enjoy stable lifetimes. Planetary systems might never survive long enough for life to emerge. The universe would contain plenty of matter, but almost no opportunity for complexity. Now imagine the opposite extreme. Suppose those primordial fluctuations had been only slightly smaller. Gravity would struggle to overcome the expansion of space. Matter would remain spread almost perfectly evenly throughout the cosmos. Gas clouds would never become dense enough to ignite nuclear fusion. No stars, no galaxies, no heavy elements, no carbon, no oxygen, no planets, no observers. The universe would remain an immense cold fog, drifting endlessly through expanding space. Neither extreme resembles the cosmos we inhabit. Instead, the fluctuations occupied an astonishingly narrow range. Large enough for gravity to build structure, small enough to prevent immediate collapse. Somehow, the universe emerged balanced between chaos and emptiness. This remarkable balance has inspired decades of scientific discussion. Physicists often describe it using the phrase fine-tuning. The term does not imply intentional design. Rather, it describes situations in which small changes to physical conditions produce dramatically different outcomes. The early universe appears to exhibit exactly this sensitivity. Tiny differences in initial density would have rewritten cosmic history completely. Why those conditions existed remains one of modern cosmology's greatest unanswered questions. Some researchers argue that inflation naturally explains the observed smoothness. Others suggest that many universes with different initial conditions may exist, and we naturally find ourselves inside one capable of supporting observers. Still others suspect that a deeper physical law, one not yet discovered, determines these values inevitably. At present, no consensus exists. The mystery remains open. Fortunately, the universe preserved a record of those earliest moments. The cosmic microwave background, often called the oldest light in the universe, acts like a fossil photograph of cosmic infancy. Although invisible to human eyes, sensitive satellites such as COBE, WMAP, and Planck have mapped its temperature. With extraordinary precision, those maps reveal faint patterns of hotter and colder regions spread across the sky. The differences are astonishingly small, only about 1 part in 100,000. Yet those tiny variations correspond almost perfectly to the seeds from which today's galaxies eventually formed. Every spiral galaxy, every elliptical galaxy, every galaxy cluster, every supercluster, every cosmic filament, all originated from fluctuations so subtle they barely disturbed the otherwise smooth young universe. It is difficult to imagine a more profound example of cause and effect. Tiny quantum events occurring during the universe's first instant eventually determined the distribution of hundreds of billions of galaxies, billions of years later. In a very real sense, the universe's largest structures remember their quantum origin. Even more surprising, The vast emptiness surrounding those structures remembers it as well. Where the early universe was slightly denser, gravity gathered matter. Where it was slightly less dense, matter gradually drained away. Over billions of years, these underdense regions expanded into the enormous cosmic voids we observe today. The emptiness was not created suddenly. It grew patiently. Gravity built islands of galaxies while simultaneously enlarging the oceans between them. The universe sculpted itself. Matter flowed toward density. Emptiness flowed toward emptiness. The contrast became sharper with every passing billion years. Today, the observable universe resembles a gigantic three-dimensional web. Thin filaments packed with galaxies stretch across incomprehensible distances. Between them lie immense voids containing almost nothing. Remarkably, both the galaxies and the emptiness trace their origins back to the same tiny quantum fluctuations imprinted during inflation. One process created everything, both structure and silence. Yet the story is still incomplete because another invisible force has quietly been reshaping this cosmic architecture for billions of years. Gravity works to gather matter together. But something else is pushing space apart. Something that neither Einstein nor the earliest cosmologists expected. An invisible influence now known as dark energy. If gravity built the universe's magnificent structures, dark energy may ultimately determine their fate. And as we are about to discover, it is steadily enlarging the greatest feature of the cosmos. Not its galaxies, but its emptiness. If you could leave the Milky Way, continue traveling beyond every neighboring galaxy, beyond every galaxy cluster, beyond distances so vast that millions of light years became ordinary, you might expect to find a universe where galaxies are scattered randomly across space, like grains of sand tossed across an endless desert. That would seem reasonable. After all, explosions scatter fragments randomly. And if the Big Bang had simply thrown matter outward, randomness would appear to be the natural outcome. But when astronomers finally learned how to map the universe on its largest scales, they discovered something entirely different. The galaxies were not scattered randomly. They were connected, not loosely, not occasionally, but throughout the observable universe, stretching across hundreds of millions of light years. Instead of chaos, the cosmos possessed structure, an enormous hidden architecture, a framework so vast that no human mind could ever fully visualize it. Today, astronomers call it the cosmic web. It is often described as the largest known structure in the universe. But perhaps a better description is this. It is the skeleton upon which the visible universe was built. The existence of this cosmic framework was not immediately obvious. For centuries, astronomers could only observe individual stars and nearby galaxies. Even after Edwin Hubble revealed that the Milky Way was merely one galaxy among countless others, the larger pattern remained invisible. The universe was simply too immense. No telescope could capture enough galaxies at once. Only during the late 20th century did massive galaxy surveys begin revealing the true picture. Projects such as the CFA Redshift Survey, followed by the 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey, measured the positions of millions of galaxies across enormous volumes of space. As computers assembled these observations into three-dimensional maps, something extraordinary emerged. The galaxies traced long, interconnected filaments. These filaments crossed the cosmos like enormous highways. Where several filaments intersected, giant galaxy clusters formed. Between them lay immense regions containing almost nothing. The universe resembled a gigantic three-dimensional spiderweb, or perhaps the branching roots of an ancient tree. The discovery surprised nearly everyone. Nature had organized itself into an intricate network spanning the observable universe. But another mystery immediately appeared. What built this colossal structure? Ordinary matter alone could not explain it. There simply was not enough visible mass. Gravity acting only on stars and gas would never have assembled such enormous filaments within the available cosmic time. Something unseen had to be shaping the universe. Something invisible. That invisible architect is known as dark matter. Unlike ordinary matter, dark matter does not emit light. It does not absorb light. It does not reflect light. No telescope has ever photographed it directly. Yet its gravitational influence appears everywhere. Galaxies rotate too rapidly to remain intact without additional unseen mass. Galaxy clusters bend light more strongly than visible matter alone can explain. The cosmic web itself follows patterns predicted by enormous halos of invisible matter. Today, cosmologists estimate that ordinary matter accounts for only about 5% of the universe's total energy content. Dark matter contributes roughly 27%. The remaining majority belongs to dark energy, whose role we will explore later. Although invisible, dark matter acts like the scaffolding surrounding a building under construction. Long before stars existed, long before galaxies formed, vast clouds of dark matter had already begun gathering under gravity. These invisible concentrations gradually attracted ordinary gas. Hydrogen flowed toward them, helium followed. Over hundreds of millions of years, gravity compressed these gases until the first stars ignited. Galaxies were born not randomly, but wherever dark matter had already prepared the foundations. In a profound sense, every visible galaxy inhabits an invisible gravitational home. Without dark matter, the cosmic web as we know it might never have formed. Imagine constructing a suspension bridge. From a distance, the roadway attracts attention. Cars travel across it. People walk upon it. But hidden beneath the visible structure lies a framework of steel cables, supporting everything above. The cosmic web behaves similarly. The galaxies are merely the illuminated roadway. Dark matter forms the hidden cables. We observe the lights. Gravity reveals the framework. Computer simulations have reinforced this remarkable picture. When cosmologists begin with conditions measured from the cosmic microwave background and allow gravity to operate for billions of years, something astonishing happens. The simulations naturally produce enormous filaments, intersections, clusters, and gigantic voids almost identical to those observed across the real universe. The resemblance is so striking that simulation images are often nearly indistinguishable from astronomical surveys. Gravity alone, acting upon the invisible distribution of dark matter, appears capable of sculpting the universe's immense architecture. This process unfolded slowly, patiently. The cosmic web was not created overnight. Following the Big Bang, the universe remained remarkably smooth. Tiny density differences, only about 1 part in 100,000, served as the initial blueprint. Over billions of years, gravity amplified those differences. Regions slightly denser than average, attracted more matter. As they grew heavier, their gravitational pull strengthened. They attracted still more matter. The rich became richer. The empty became emptier. Gradually, matter flowed away from underdense regions toward growing filaments. The web sharpened, the voids expanded, the contrast increased. Even today, the process continues. Gravity never truly stops working. Every galaxy drifting along a filament participates in this ongoing cosmic construction project. Every cluster continues gathering new members. Every void slowly grows larger. The cosmic web remains alive. One of its most surprising characteristics is where galaxies actually exist. Popular illustrations often depict galaxies floating freely throughout space. Reality is very different. Galaxies overwhelmingly inhabit the filaments. Like cities built along rivers, they follow invisible pathways determined by gravity. The vast spaces between those pathways contain astonishingly few galaxies. Imagine flying across North America at night. Bright ribbons of city lights trace coastlines and highways. Between them lie enormous dark regions. The cosmic web resembles something similar, except on scales hundreds of millions of light-years across. Light gathers along the filaments. Darkness dominates everything else. Those dark regions are known as cosmic voids. Some extend across more than 300 million light-years. Within them, galaxies become extraordinarily rare. A traveler crossing such a void might journey for millions of light-years without encountering a single large galaxy. The universe's greatest structures are therefore defined not only by where matter exists, but by where it does not. The emptiness has shape. The voids are as important to the cosmic web as the filaments themselves. Without emptiness, the web could not exist. This realization leads to an unexpected comparison. Over the past 2 decades, several researchers noticed that visualizations of the cosmic web bear a striking resemblance to another familiar structure: the human brain. Neurons branch outward through intricate networks. Dense clusters connect by long filaments. Large, empty regions separate those connections. At first glance, images of the cosmic web and microscopic neural tissue appear surprisingly similar. The resemblance quickly attracted widespread attention. Could the universe somehow organize itself like a gigantic brain? The comparison is fascinating, but caution is essential. The similarity is primarily visual. Neural networks in the cosmic web arise through entirely different physical processes. Brains evolve through biology and chemistry. The cosmic web forms through gravity, acting upon dark matter across billions of years. No evidence suggests that the universe functions as a literal brain. Nevertheless, the resemblance illustrates something profound. Nature often produces similar patterns, despite operating under completely different laws. Tree branches, river systems, lightning, blood vessels, neural networks, galactic filaments. Each emerges from simple rules repeated over enormous scales. Complexity often grows from astonishingly simple beginnings. Gravity pulls, matter responds, time does the rest. Perhaps the greatest lesson of the cosmic web is that the universe possesses order far beyond immediate perception. From Earth's surface, the night sky appears random. Constellations are human inventions. Stars seem scattered without design. Only by stepping far beyond our local perspective do we begin seeing the larger architecture. The same principle appears repeatedly throughout science. Atoms possess hidden structure. Solar systems belong to galaxies. Galaxies belong to filaments. Filaments belong to the cosmic web. Reality reveals increasing layers of organization as our perspective expands. Yet there remains another invisible force quietly transforming this magnificent structure. Gravity built the web. Dark matter provided its framework. But something else is now pulling the filaments farther apart. The voids continue expanding. The distances between galaxy clusters steadily increase. The cosmic web itself is gradually being stretched. The universe is not freezing into a permanent pattern. Its greatest architecture is still evolving, slowly, silently, almost imperceptibly, and the force responsible for this transformation may ultimately determine the fate of every galaxy, every star, and every civilization that will ever exist. It is called dark energy. And while gravity spent billions of years weaving the universe together, dark energy may spend trillions of years pulling it apart. If the cosmic web forms the skeleton of the universe, then the vast spaces between its filaments are not simply empty gaps. They are enormous structures in their own right. Structures so immense that entire galaxy clusters could disappear inside them without significantly changing their appearance. These are known as cosmic voids. At first, the name seems almost disappointing. A void, an absence, a place where almost nothing exists, but appearances can be deceiving. Some of the greatest discoveries in modern cosmology have come not from studying what fills the universe, but from studying what does not, because the largest structures ever discovered are not galaxies, not galaxy clusters, not even the cosmic web itself. They are the immense regions where almost everything is missing. Imagine leaving the Milky Way and traveling across intergalactic space. Millions of light years pass beneath your spacecraft. Galaxies become fewer. The brilliant rivers of the cosmic web begin to fade behind you. Eventually, even neighboring galaxies disappear. Ahead lies only darkness. Not the darkness of night, the darkness of absence. For millions of light years in every direction, almost nothing interrupts the emptiness. You have entered a cosmic void. These regions are difficult to appreciate because human intuition evolved in environments where empty spaces are relatively small. A valley may seem enormous, an ocean may appear endless. Even the vast emptiness between stars stretches the imagination. Cosmic voids make all of these comparisons meaningless. Some are so large that light itself requires hundreds of millions of years to cross them. One of the most famous examples is the Bootes void. Discovered in 1981, it immediately challenged astronomers' expectations about the universe. The Bootes void spans roughly 330 million light-years. To appreciate that scale, remember that the Milky Way measures only about 100,000 light-years across. More than 3,000 galaxies the size of our own could be lined up side by side before reaching the opposite edge of this immense emptiness. If our solar system occupied one side of the Bootes void, the light leaving the sun today would not reach the opposite side until long after every civilization currently on Earth had vanished into history. Yet despite its unimaginable size, the Bootes void is not completely empty. Early reports sometimes described it as containing almost no galaxies at all. Modern observations have revealed that dozens of galaxies do exist inside it. Compared with the surrounding universe, however, their numbers are astonishingly small. Imagine walking through an enormous forest and suddenly finding yourself inside a clearing hundreds of kilometers wide, containing only a handful of isolated trees. That is the difference between a cosmic filament and the Boots void. The emptiness is defined not by the complete absence of matter, but by its extraordinary scarcity. Another remarkable example lies in the direction of the constellation Eridanus. Astronomers call it the Eridanus supervoid. Its estimated size approaches or exceeds 1 billion light-years, depending on exactly how its boundaries are defined. Unlike the Bootes void, the Eridanus supervoid became famous for another reason. It may be connected to one of the strangest features ever observed in the cosmic microwave background. Satellite observations have revealed a mysterious region known as the cold spot. This area appears slightly cooler than surrounding regions of the ancient radiation left behind by the Big Bang. One possible explanation suggests that light traveling through the enormous Eridanus supervoid loses a tiny amount of energy as the universe expands. If true, the void itself may have left a measurable imprint on radiation that has traveled for nearly 14 billion years. The explanation remains debated. Some researchers argue that the supervoid alone cannot fully account for the cold spot. Others suggest that several overlapping structures may contribute. Whatever the final answer, the discussion highlights an extraordinary fact. Even regions containing almost nothing can influence the appearance of the universe on its largest observable scales. The absence of matter can become scientifically important. This raises another fascinating question. How empty is a void, really? The word suggests perfect nothingness. Reality is considerably more subtle. Cosmic voids are not giant bubbles carved out of absolute emptiness. Instead, they contain matter at densities far below the cosmic average. Small galaxies continue drifting through them. Thin clouds of hydrogen gas remain scattered across their enormous volumes. Invisible dark matter still extends throughout these regions, although in much smaller concentrations than inside the surrounding filaments. Even the quantum vacuum remains active, filled with microscopic fluctuations, continuously appearing and disappearing. A cosmic void is therefore not empty in the philosophical sense. It is empty only relative to the rich structures surrounding it. This distinction matters because complete emptiness may not exist anywhere in the universe. The voids are remarkable precisely because they approach that ideal more closely than almost any other known environment. One might wonder why these enormous regions formed at all. The answer lies in gravity's relentless tendency to amplify differences. Soon after the Big Bang, the universe contained tiny variations in density. Regions slightly denser than average attracted additional matter. As gravity strengthened those concentrations, neighboring underdense regions gradually lost material. Matter flowed outward toward the growing filaments of the cosmic web. Over billions of years, the dense regions became richer. The sparse regions became poorer. The result was not merely the formation of galaxies. It was the gradual evacuation of the spaces between them. In an extraordinary sense, cosmic voids did not simply remain empty. They were emptied. Gravity continuously removed matter from these regions, transporting it toward the invisible highways of the cosmic web. The process continues today. Galaxies located near the edges of voids slowly drift towards surrounding filaments under the influence of gravity. Meanwhile, the interiors become increasingly underdense. The universe appears to be separating itself into two contrasting domains. Dense structures grow denser, empty regions grow emptier. This evolution has profound consequences for the future of the cosmos. Computer simulations reveal that voids expand more rapidly than the universe's average expansion. Because they contain relatively little matter, gravity offers less resistance to the stretching of space. As the universe expands, voids naturally inflate. Neighboring voids merge together. Their boundaries shift. Their volumes increase. Over billions of years, the empty regions consume an ever larger fraction of cosmic space. Ironically, the universe is becoming increasingly dominated by its emptiest places. Galaxies remain trapped within thin filaments while the surrounding voids continue growing around them. Some cosmologists describe this process as a kind of cosmic foam. Imagine soap bubbles pressed together. The thin walls separating them resemble the galaxy-rich filaments. The interiors resemble the expanding voids. The resemblance is not perfect, but it captures an essential truth. Most of the universe's volume belongs not to galaxies, but to the immense bubbles surrounding them. This expanding emptiness also influences how astronomers measure the universe. Light traveling through a void experiences slightly different gravitational conditions than light passing through dense galaxy clusters. Tiny changes accumulate across billions of light years. The paths of photons bend differently. Their energies shift subtly. Modern cosmological surveys must account for these effects when reconstructing the universe's large-scale geometry. Even the emptiest regions participate in shaping what we observe. In recent years, researchers have begun using cosmic voids as powerful laboratories for testing fundamental physics. Because voids contain relatively little matter, they provide exceptionally clean environments for studying gravity. Alternative theories attempting to replace Einstein's general relativity often predict small differences in how galaxies move near the edges of voids. Future galaxy surveys may therefore use these immense empty regions to test competing models of gravity itself. Ironically, the best place to search for new physics may be where almost nothing exists. The universe repeatedly teaches the same lesson. Absence can be as informative as presence. Silence can speak. Emptiness can reveal. The voids also force us to reconsider our emotional relationship with the cosmos. When we imagine the universe, we usually picture brilliant spiral galaxies glowing against the darkness. But those luminous islands occupy only a tiny fraction of the total volume. Most of existence unfolds far away from any galaxy, far from stars, far from planets, far from the chemistry that makes life possible. If an intelligent civilization somehow evolved inside a deep cosmic void, its night sky might appear profoundly different. Neighboring galaxies would be vastly more distant. The universe itself could seem lonelier than anything we can currently imagine. Perhaps the greatest irony of cosmic voids is this: they appear empty because gravity has succeeded. Every galaxy concentrated inside the surrounding filaments represents matter that once occupied those empty regions. The voids are not failures of cosmic evolution. They are its inevitable consequence. Gravity gathered, space separated, time amplified the difference. And throughout billions of years, the largest structures in the universe quietly became larger still. Yet gravity is no longer the only force shaping this evolution. Another influence has begun dominating the cosmos, one that does not gather matter together, but instead stretches space itself. An invisible phenomenon accelerating the expansion of every void, increasing the distance between every filament, and slowly isolating every galaxy from every other. It is called dark energy. And if gravity built the universe's magnificent architecture, dark energy may ultimately dissolve it into an even greater emptiness than the cosmos has ever known. For most of the 20th century, astronomers believed they understood the future of the universe. Gravity, they reasoned, was the ultimate ruler of cosmic evolution. Every galaxy attracted every other galaxy. Every cluster pulled upon its neighbors. The expansion that began with the Big Bang should gradually slow as gravity fought against it. The only uncertainty seemed to be how much it would slow. Would gravity eventually stop the expansion completely? Would the universe expand forever, becoming slower and slower? Or would everything reverse in a colossal collapse known as the Big Crunch? For decades, these were considered the only serious possibilities. Then, in 1998, the universe delivered one of the greatest surprises in the history of science. It was not slowing down. It was speeding up. The discovery came from two independent teams of astronomers studying one of the brightest explosions in the cosmos, Type Ia supernovae. These stellar explosions occur when white dwarf stars reach a critical mass and explode with nearly identical intrinsic brightness. Because they shine with such predictable luminosity, astronomers can use them as standard candles, measuring enormous cosmic distances by comparing how bright they appear from Earth. The farther away the supernova, the longer its light has traveled, the dimmer it appears. By combining these distance measurements with observations of galactic redshift, scientists hoped to determine how gravity had influenced the universe's expansion over billions of years. The results made almost no sense. The distant supernovae were dimmer than expected. Not slightly, consistently. The simplest explanation was astonishing. The expansion of the universe had not been slowing. It had been accelerating. Some invisible influence was overcoming gravity itself. Instead of pulling galaxies back together, the universe was pushing them farther apart. That mysterious influence became known as dark energy. Today, more than a quarter of a century after its discovery, dark energy remains one of the greatest mysteries in all of science. Astronomers estimate that it accounts for approximately 68% of the total energy content of the universe. Ordinary matter, the stars, planets, gas, dust, and every living creature, accounts for less than 5%. Dark matter contributes roughly 27%. Everything we have ever seen represents only a tiny fraction of reality. The dominant component of the cosmos remains invisible. Even more remarkable, we still do not know what it actually is. To understand why dark energy changes everything, we must first rethink one of our deepest assumptions. When galaxies move farther apart, it is natural to imagine them flying through space like fragments from an explosion. But that picture is misleading. Galaxies are not simply moving through space. Space itself is expanding. Imagine drawing dots across the surface of a rubber balloon. Each dot represents a galaxy. As the balloon inflates, every dot moves away from every other dot. The dots themselves are not crawling across the rubber. The surface beneath them is stretching. Our universe behaves in much the same way. The distances between galaxies increase because space-time itself expands. This distinction becomes crucial. Dark energy is not pushing galaxies outward like a giant cosmic wind. Instead, it appears to influence the expansion of space itself. Every billion light-years of space slowly becomes larger. As the universe grows, additional space forms between distant galaxies. The farther apart two galaxies already are, the more rapidly this expansion increases their separation. This explains one of the most surprising observations in cosmology. Very distant galaxies can appear to recede from us faster than the speed of light. At first glance, this seems impossible. Einstein taught us that nothing can travel faster than light. And Einstein remains correct. The galaxies themselves are not breaking that limit. They are not racing through space faster than light. Instead, the space between us and those galaxies is expanding. General relativity permits space-time itself to stretch without obeying the familiar speed limit that governs motion through space. The distinction is subtle, but essential. The universe is not violating relativity. It is behaving exactly as relativity predicts. As dark energy continues driving cosmic expansion, another extraordinary boundary emerges. The cosmic horizon. Imagine standing beside the ocean, watching a ship disappear over the horizon. Eventually, the ship becomes invisible. Not because it has ceased to exist, but because Earth's curvature hides it from view. The universe possesses a similar boundary. Not because space curves around us, but because expansion carries distant galaxies away faster than their light can eventually reach us. Every year, more galaxies cross this invisible horizon. They still exist. They continue evolving. Stars continue forming inside them. Civilizations, if any exist, continue living their histories. Yet their future light will never arrive here. Not because the galaxies have stopped shining, but because space between us expands too rapidly. In a profound sense, the observable universe is gradually shrinking, not physically, visually. More and more of the cosmos becomes permanently unreachable. This process unfolds incredibly slowly on human timescales. But across billions of years, its consequences become astonishing. Today, astronomers estimate that roughly 2 trillion galaxies may exist within the observable universe. Future civilizations will inherit a very different sky. Most galaxies beyond our own local neighborhood will eventually disappear forever. The Great Spiral Galaxy, Andromeda, will not vanish. Neither will the smaller members of the local group. Gravity binds these galaxies together strongly enough to overcome cosmic expansion. In fact, the Milky Way and Andromeda are already moving toward one another. Approximately 4 to 5 billion years from now, they are expected to collide, eventually merging into a single enormous galaxy. Dark energy cannot separate structures already held together by sufficiently strong gravity. Solar systems remain intact. Galaxies remain intact. Galaxy clusters can remain intact. The expansion acts primarily across the immense distances separating these gravitationally bound systems. Everything larger slowly drifts apart. Everything smaller remains together. This distinction explains why we do not notice the universe expanding inside our own galaxy. The solar system is not growing larger. Earth is not drifting away from the sun. Your body is not expanding. Gravity, and at smaller scales, electromagnetic forces, overwhelms the incredibly weak influence of cosmic expansion. Dark energy dominates only across enormous distances where gravity becomes comparatively weak. Yet even this limited influence profoundly changes the long-term future of the cosmos. Imagine an astronomer living 100 billion years from now. The local group has already merged into a single giant galaxy. Every other galaxy has crossed the cosmic horizon. The night sky appears almost empty. No distant galaxies remain visible. The cosmic microwave background has stretched into wavelengths too long to detect. Even the evidence for the Big Bang has largely disappeared. From that future astronomer's perspective, the universe may appear static, isolated, alone. Ironically, they might conclude that their galaxy constitutes the entire universe. The greatest discoveries of 20th and 21st century cosmology would become almost impossible to reconstruct. History itself would have erased its own evidence. This remarkable prediction reveals something deeply unsettling. We happen to live during a uniquely privileged era of cosmic history. The universe is old enough for galaxies to have formed, yet young enough that we can still observe billions of them. The cosmic microwave background remains detectable. The expansion remains measurable. Future observers may lose access to all of these clues forever. In that sense, modern cosmology may be living through a brief golden age. The universe is still revealing its history. It will not always do so. Dark energy is quietly closing the window. The emotional implications are difficult to ignore. Humanity has always feared isolation. Ancient civilizations worried about lonely oceans. Modern explorers crossed continents seeking distant cultures. Astronomers searched the stars for signs of intelligent life. Yet the universe itself appears to be moving steadily toward greater solitude. Not because civilizations are disappearing, not because galaxies are dying, but because the expanding fabric of space-time increasingly separates everything from everything else. The cosmos is becoming more isolated with every passing second. This isolation extends beyond philosophy. It has measurable physical consequences. Light emitted today by sufficiently distant galaxies will never reach us. Signals we transmit today will never reach enormous portions of the observable universe. Entire regions of reality have already become permanently disconnected. The cosmic conversation grows quieter with time. Yet, perhaps the greatest irony of dark energy is that it also made our existence possible. If cosmic expansion had remained too weak, gravity might eventually have collapsed the universe before life had sufficient time to evolve. If expansion had always been too strong, galaxies themselves might never have formed. Instead, the universe spent billions of years balanced delicately between these extremes. Only relatively recently, after galaxies, stars, planets, and life had already emerged, did dark energy begin dominating cosmic evolution. The timing appears almost astonishing. Whether this represents coincidence, necessity, or something deeper remains one of modern cosmology's great unanswered questions. Scientists continue searching for answers. Some suspect dark energy represents the energy of empty space itself, the cosmological constant first introduced by Einstein. Others propose entirely new quantum fields permeating the universe. Still others wonder whether general relativity itself requires modification across cosmic distances. No consensus yet exists. Dark energy remains one of the greatest unsolved mysteries in physics. We know it exists because we observe its effects. We know it dominates the universe. But we do not yet understand its true nature. Perhaps future observatories will finally reveal its identity. Perhaps entirely new physics awaits discovery. Until then, one fact remains unavoidable. The universe is not simply expanding. It is accelerating into greater emptiness. Every year, more galaxies drift beyond our reach. Every billion years, the cosmic web stretches farther apart. Every trillion years, the observable universe grows lonelier. The greatest emptiness in the cosmos is no longer merely the voids between galaxies. It is the future itself. A future in which nearly every island of light becomes permanently isolated from every other. And nowhere is that isolation more personal than our own cosmic neighborhood. Because while the rest of the universe slowly disappears beyond the horizon, the small family of galaxies known as the local group may become humanity's final island in an endlessly expanding sea of darkness. For thousands of years, humanity believed the universe was simply waiting to be explored. Beyond every horizon, there would always be another ocean, another continent, another mountain, another star. Every generation inherited a larger map than the one before it. The history of civilization has been the history of expanding horizons. But modern cosmology has revealed a deeply unsettling truth. There is one horizon that no civilization, no matter how advanced, will ever cross. Not because of technological limitations, not because of insufficient time, but because the universe itself forbids it. We often imagine the observable universe as though it were the entire cosmos. It is not. The observable universe is simply the region from which light has had enough time to reach us since the Big Bang. Its current radius is about 46.5 billion light-years. Everything beyond that distance remains invisible. Not necessarily because it does not exist, but because its light has not yet had sufficient time to arrive. This distinction is crucial. The observable universe is not a physical boundary. It is an observational one. There may be vastly more universe beyond it, perhaps infinitely more. We simply cannot see it. Already, this places humanity inside a kind of cosmic bubble. But there is another boundary that is even more profound. Unlike the observable universe, this second horizon is not merely temporary. It is permanent. Cosmologists call it the cosmic event horizon. The name echoes another famous boundary we encountered earlier: the event horizon of a black hole. The comparison is not accidental. Both horizons separate events that can still influence us from those that never will. Imagine standing on a beach as the tide carries bottles farther out to sea. Some remain close enough that a wave might eventually return them. Others drift beyond a powerful current. No matter how long you wait, they will never come back. The expanding universe behaves in much the same way. Galaxies sufficiently distant today are being carried away by the expansion of space itself. Their future light will never reach Earth. They have crossed a cosmic point of no return. This is one of the strangest consequences of dark energy. The universe is not simply becoming larger. It is becoming permanently inaccessible. Every second, more galaxies disappear beyond the cosmic event horizon. They continue existing. Stars continue shining. Planets continue orbiting. If intelligent civilizations inhabit those galaxies, they continue asking questions beneath their own night skies. Yet, from our perspective, they have become forever unreachable. No spacecraft, no laser, no radio transmission. No technology permitted by known physics can ever bridge the growing separation. The universe is quietly isolating its islands of matter. To appreciate the scale of this isolation, consider our own cosmic neighborhood. The Milky Way belongs to a small collection of galaxies known as the Local Group. It contains more than 100 known members, including the Andromeda Galaxy, the Triangulum Galaxy, and numerous dwarf galaxies. Unlike the rest of the universe, these galaxies remain gravitationally bound. Gravity overwhelms the relatively weak effects of cosmic expansion across these comparatively short distances. In fact, Andromeda is moving toward us at approximately 110 kilometers per second. Several billion years from now, the Milky Way and Andromeda will collide, not in a violent head-on crash of stars. Space is far too empty for that, but through a slow gravitational dance lasting billions of years. Eventually, the two galaxies will merge into one enormous elliptical system. Astronomers sometimes call this future galaxy Milkomeda. Long after that merger is complete, the local group will remain together. Everything beyond it, however, gradually slips away. The nearby Virgo cluster, gone. The Coma cluster, gone. Every magnificent spiral galaxy now visible through modern telescopes, gone. Not because they have been destroyed, because space itself has stretched so dramatically that their light can no longer overcome the expansion. One by one, they disappear. Imagine standing beneath today's night sky. Thousands of galaxies surround the Milky Way, invisible to the naked eye, but easily photographed by modern observatories. Now imagine watching time accelerate. Millions of years pass in moments, hundreds of millions, billions. The universe slowly empties. Galaxy clusters fade. Distant spirals grow dim. The great filaments of the cosmic web dissolve into darkness. Eventually, only the local group remains. Everything else has slipped beyond the horizon. The universe becomes smaller, not in reality, only in what can be observed. Now, carry this thought much farther. Imagine an astronomer living 100 billion years from now. Civilizations may have risen and fallen countless times. Stars like our Sun have long since died. The Milky Way and Andromeda have completely merged. The night sky reveals only one enormous galaxy surrounded by darkness. No external galaxies remain visible. The cosmic microwave background, the oldest light in the universe, has been stretched by cosmic expansion into wavelengths so enormous that it becomes effectively undetectable. Even the evidence that the universe once expanded has vanished. From this future astronomer's perspective, the cosmos appears static, isolated, timeless. They might conclude that their single galaxy constitutes the entire universe. The Big Bang itself could become impossible to discover. This realization carries profound implications. Scientific knowledge depends upon evidence. If the evidence disappears, some truths become permanently inaccessible. Future civilizations may never reconstruct the true history of the cosmos, not because they lack intelligence, but because the universe has hidden its own past. We often imagine science as an endless march toward complete understanding. Cosmology teaches something more humbling. Some knowledge has an expiration date. We happen to exist during a brief era when the universe still reveals its history. That window will not remain open forever. This means humanity occupies an extraordinarily fortunate moment in cosmic history. The universe is approximately 13.8 billion years old. Stars have already produced the heavy elements necessary for life. Galaxies have fully developed. Dark energy has begun dominating cosmic expansion, but not yet enough to erase the evidence of our origins. We live during the narrow interval when both the beginning and the large-scale structure of the universe remain observable. Past and present briefly overlap. Future astronomers may inherit only fragments. This naturally leads to another remarkable conclusion. Humanity will never know the entire universe, not because we lack better telescopes, not because interstellar travel is difficult, because the observable universe itself represents only part of reality. There may be regions forever beyond our reach. Perhaps the universe extends infinitely. Perhaps entirely different cosmic structures exist beyond the observable horizon. Perhaps the laws of physics vary elsewhere. We simply cannot know. The cosmic event horizon establishes a permanent limit on observation. Some questions may remain forever unanswered. This idea can feel deeply unsettling. Human curiosity naturally resists boundaries. Throughout history, every apparent frontier eventually yielded to exploration. Mountains were crossed, oceans were sailed, planets were reached. The cosmic horizon is different. It cannot be crossed because it is not an obstacle located somewhere ahead. It is a consequence of space-time itself. As the universe expands, the horizon expands too. It always remains beyond reach. No matter how advanced a civilization becomes, there will always be regions forever inaccessible. In this sense, the universe possesses secrets that may never be revealed. Yet perhaps the most powerful lesson is philosophical rather than scientific. We often think of loneliness as a human experience, a feeling belonging to individuals. Cosmology suggests that loneliness may also characterize the universe itself. Every galaxy gradually becomes an island. Every island drifts farther from every other. Communication becomes impossible. Eventually, even the memory of neighboring galaxies may disappear. The universe grows quieter. Not because life necessarily vanishes, but because distance triumphs over connection. And yet, there is another way to view this story. The same expansion isolating galaxies also created the conditions allowing them to exist in the first place. Without billions of years of cosmic evolution, stars would never have forged carbon. Planets would never have formed. Life would never have emerged. The emptiness separating galaxies is not merely the source of future isolation. It is also the reason complexity became possible. Creation and loneliness arise from the same cosmic process. Perhaps that is the deepest paradox of all. The universe made us possible by ensuring that everything would eventually become separated. Our existence is therefore inseparable from our isolation. Every observer in the cosmos inhabits a temporary island of light surrounded by expanding darkness. Every civilization exists during a brief chapter when the universe remains knowable. Every generation receives a window that slowly closes behind it, and perhaps that realization changes the meaning of exploration itself. We no longer explore because the universe is limitless. We explore because our opportunity is limited, because there are discoveries that can only be made now. questions that can only be answered during this brief moment in cosmic history. The horizon is moving, the evidence is fading. The universe is growing quieter, and somewhere beyond the darkness, countless galaxies continue their silent journeys forever beyond our reach. Their light will never reach us. Their stories will never be told. Not because they do not exist, but because the expanding universe has chosen to keep them forever beyond humanity's final horizon. Imagine rewinding the history of the universe. The galaxies disappear, the stars fade away. Atoms dissolve into a sea of elementary particles. Time races backward until the universe is only fractions of a second old. Now imagine changing just one thing, not dramatically, not by half, not even by 1%. Only a tiny adjustment to the initial density of matter. So small that no human instrument could have measured it at the moment of the Big Bang. Would the universe still look like ours? Modern cosmology gives a remarkable answer. Probably not. Everything we have ever known may depend on a balance so delicate that changing it ever so slightly would create an entirely different cosmos. This is one of the deepest lessons hidden within the emptiness of space. The universe is not merely empty. It appears to be precisely empty enough. Let us begin with the first possibility. Imagine a universe that emerged from the Big Bang only slightly denser than our own. At first, the difference seems insignificant. A little more matter, a little stronger gravity, nothing dramatic. But gravity is not a force that simply adds up. It amplifies itself. A region that is slightly denser attracts more matter. As more matter arrives, gravity becomes stronger. That stronger gravity attracts even more matter. The process feeds upon itself. Over millions of years, then billions, small differences become enormous ones. In this denser universe, gravity would dominate much earlier. Gas clouds would collapse rapidly. Galaxies would grow larger and more violently. Massive stars would form in overwhelming numbers. Their short lives would end in supernova explosions and black hole formation. Entire regions of the universe might collapse directly into enormous black holes before stable planetary systems ever had time to develop. The night sky would still shine, perhaps even more brilliantly than our own. But its beauty would conceal instability. Stars would be born too quickly. Galaxies would collide too often. Radiation would flood young planetary systems. The universe would become a place where complexity struggled to survive. Some cosmological models suggest that sufficiently large density fluctuations could have transformed much of the early universe into what researchers sometimes call a black hole-dominated universe. Instead of countless long-lived galaxies connected by the cosmic web, gravity would have concentrated matter into enormous gravitational traps. Structure would still exist. Life, however, might never have had a realistic opportunity to emerge. Now let us imagine the opposite extreme. Suppose the early universe contained slightly less matter, only a little less. The immediate effect would seem harmless. Gravity would simply become a bit weaker. But once again, gravity amplifies tiny differences over cosmic time. In this universe, gas clouds would struggle to collapse. The first stars would form much later, perhaps not at all. Without stars, there would be no stellar furnaces producing carbon, oxygen, silicon, or iron. No rocky planets, no oceans, no chemistry capable of supporting life. The universe would remain a cold ocean of hydrogen and helium, expanding into endless darkness. Astronomers sometimes describe this scenario as a no-galaxy universe. Not because galaxies are impossible in principle, but because the initial conditions never allow gravity to gather matter efficiently enough to build them. The universe would be extraordinarily simple. Beautiful, perhaps, but empty of observers, empty of questions, empty of stories. Our own universe exists between these two extremes, not too dense, not too empty. Gravity is strong enough to assemble galaxies, weak enough to avoid immediate collapse. Stars live long enough for planets to form. Planets remain stable long enough for chemistry to become biology. Biology eventually becomes intelligence. And intelligence asks why the universe appears so carefully balanced. This remarkable sensitivity is known as fine-tuning. The phrase often generates misunderstanding. It does not necessarily imply intention or design. Instead, it describes a scientific observation. Certain physical parameters appear to occupy extraordinarily narrow ranges that allow complex structures to exist. Change those values too much, and the universe becomes dramatically different. Density is only one example. The strength of gravity, the mass of the electron, the strength of the strong nuclear force, the expansion rate of the early universe. Many fundamental constants appear to possess values permitting stars, chemistry, and ultimately life. Whether this represents coincidence, necessity, or something deeper remains one of the greatest open questions in physics. One proposed explanation is known as the anthropic principle. Despite its intimidating name, the basic idea is surprisingly straightforward. We observe a universe capable of supporting observers, because only such a universe can ever be observed. Imagine billions of lottery tickets. Most lose. Only the winning ticket receives attention. Likewise, if many universes exist with different physical properties, conscious beings naturally find themselves inside one where the conditions allow consciousness to arise. The anthropic principle does not explain why the universe possesses its particular properties. Instead, it explains why observers should not be surprised to find themselves living in a universe compatible with their own existence. Some physicists consider this reasoning valuable. Others argue that it risks avoiding deeper explanations. The debate remains active. Another possibility suggests that fine-tuning may eventually disappear altogether. Perhaps future physics will reveal that the constants of nature could never have been different. What currently appears astonishing may simply reflect deeper mathematical relationships not yet understood. History offers many examples. Ancient astronomers once regarded planetary motion as mysterious. Newton revealed underlying laws. Later, Einstein revealed still deeper ones. Perhaps the apparent fine-tuning of the universe represents another invitation to discover more fundamental principles. Modern cosmology has therefore produced several competing ideas. Some researchers investigate inflationary cosmology, where countless universes may emerge with varying properties. Others pursue string theory, whose enormous landscape of possible solutions might naturally produce many different cosmic environments. Still others search for a unified theory of quantum gravity, capable of determining the constants from first principles. At present, none of these approaches has achieved universal acceptance. The evidence remains incomplete. The debate continues. Yet, regardless of which explanation ultimately proves correct, one fact remains beyond dispute. Our universe occupies an extraordinarily narrow region of possibility. It is balanced between gravitational collapse and eternal emptiness, between chaos and simplicity, between too much structure and almost none at all. Perhaps the most remarkable realization is that this balance is reflected everywhere we have looked. The galaxies are neither packed together nor scattered beyond formation. The cosmic web contains just enough matter to support magnificent structures while leaving enormous voids between them. Dark energy became dominant only after stars and planets had already formed. Even the emptiness itself appears delicately proportioned. Not absolute, not overwhelming, just sufficient to permit complexity. The terrifying emptiness surrounding us is therefore not evidence of failure. It may be evidence of extraordinary balance. A universe overflowing with matter could have destroyed itself. A universe containing too little matter might never have created anything interesting at all. Instead, we inhabit a cosmos suspended almost perfectly between those extremes. The greatest irony is impossible to ignore. Everything we cherish, stars, planets, oceans, forests, civilizations, and life itself, exists not despite the immense emptiness of the universe, but because of it. The void is not the enemy of creation. It is its silent partner. Without the emptiness, there would be no galaxies. Without the distance, there would be no stability. Without the delicate balance established during the first moments after the Big Bang, there would be no one left to wonder why the universe is so astonishingly empty. And perhaps that is the final revelation. The universe did not simply tolerate emptiness. It required it. Because in the architecture of the cosmos, the vast oceans of nothingness are not wasted space. They are the invisible foundation upon which everything else was built. When we first looked into the night sky, the universe seemed full of stars, full of galaxies, full of endless possibilities. But over the course of this journey, a very different picture has emerged. The universe is not defined by what it contains. It is defined by what separates everything within it. The vast oceans of emptiness between stars, between galaxies, between the immense filaments of the cosmic web, are not simply background scenery. They are the stage upon which the entire story of the cosmos unfolds. And if the laws of physics continue operating as they do today, that emptiness will ultimately become the universe's final victor. The story begins billions of years from now. The stars we know today will not last forever. Every star is powered by nuclear fusion. Every second, enormous quantities of hydrogen are transformed into helium. That fuel supply is finite. Large stars burn through it rapidly, living only millions of years. Smaller stars consume their fuel much more slowly. Red dwarfs, the smallest true stars, may survive for trillions of years. They will become the last luminous objects in the universe, long after galaxies have changed beyond recognition, long after the sun has disappeared. These tiny stars will continue shining quietly in the darkness, but even they cannot burn forever. Eventually, the final star will exhaust its fuel. The universe will witness its last sunrise. After that moment, no new starlight will ever naturally appear again. Astronomers call the unimaginably distant future that follows the degenerate era white dwarfs, neutron stars, and black holes dominate the cosmos. The brilliant galaxies that once illuminated the night have faded into silent collections of stellar remnants. Among those remnants are objects known as white dwarfs. These are the dense cores left behind by stars like our Sun. Today they remain hot, glowing faintly with stored thermal energy. Given enough time, far longer than the current age of the universe, they too will cool, slowly, steadily, until they emit almost no visible light at all. At that point, they become what physicists call black dwarfs. No black dwarf has ever existed. The universe is simply not old enough. But according to current models of stellar evolution, they represent the inevitable fate of nearly every sun-like star. The black dwarf era will therefore be a universe almost entirely without light, frozen. Stellar embers drifting through expanding darkness. Yet even then, the story does not end. Scattered across this increasingly empty universe remain the most extreme objects ever created. Black holes. During earlier chapters, they consumed stars, gas clouds, and even entire galaxies. They appeared almost eternal. For decades, scientists believed they might survive forever. Then Stephen Hawking revealed something extraordinary. Black holes slowly evaporate. Through Hawking radiation, they lose unimaginably tiny amounts of energy. For stellar black holes, the process requires around 10 far years. For the largest supermassive black holes, evaporation may continue for more than 10 far years. These numbers are almost beyond comprehension. Yet even eternity, it seems, has limits. Eventually, the final black hole disappears. Its last quantum of radiation escapes into the darkness. The black hole era comes to an end. What remains afterward is almost impossible to imagine. No stars, no galaxies, no planets, no black holes. Only isolated elementary particles drifting through an endlessly expanding universe. Photons travel alone across distances so enormous that they almost never encounter another particle. Temperature approaches absolute zero. Energy becomes evenly distributed. Nothing meaningful happens anymore. This is the scenario cosmologists call the heat death of the universe. The name can be misleading. The universe does not become hotter. It becomes so thoroughly uniform that no useful energy remains available to perform work. Every temperature difference disappears. Every source of order gradually dissolves. Complex structures become impossible to sustain. Another name for this future is the Big Freeze. It is not a violent ending. No final explosion. No dramatic collapse. Instead, the universe slowly fades into silence. Expansion continues. The distances between surviving particles continue growing. Time stretches onward. The cosmos becomes colder, darker, and emptier. Ironically, the very emptiness that once allowed galaxies to form now ensures that those galaxies will ultimately become isolated beyond recovery. Dark energy continues expanding space. The cosmic web slowly unravels. The immense voids grow larger still. Every remaining island of matter drifts farther from every other. The universe does not die through destruction. It dies through separation. Perhaps this is the deepest lesson hidden within cosmic emptiness. At the beginning of our journey, emptiness appeared frightening. It seemed like the absence of creation, the absence of meaning. Yet modern cosmology reveals something far more profound. Without enormous distances between stars, stable planetary systems could not exist. Without the vast spaces separating galaxies, the cosmic web would never have formed. Without the delicate balance established during the earliest moments after the Big Bang, life itself might never have emerged. Emptiness was never the enemy of creation. It was its foundation. And yet, the same emptiness that made complexity possible also shapes its eventual fate. As space continues expanding, the void grows larger. The galaxies grow more isolated. The universe becomes quieter with every passing billion years. Creation and isolation are two chapters of the same story. One cannot exist without the other. Perhaps that is why the universe feels so strangely beautiful. Its greatest strength contains the seed of its greatest loneliness. Its vast emptiness gave birth to stars, planets, oceans, life, and consciousness. Then, over unimaginable stretches of time, that same emptiness slowly reclaims everything. The universe does not merely contain the void. The void patiently shapes the destiny of the universe itself. And perhaps that is the greatest revelation of all. The most important structure in the cosmos is not a galaxy, not a black hole, not even the cosmic web. It is the immeasurable emptiness surrounding them. Because within that silence, the universe learned how to create. And within that same silence, it will one day learn how to end. As we conclude this journey across the largest scales of existence, one truth becomes impossible to ignore. The universe is far more empty than our eyes could ever reveal. Yet within that overwhelming emptiness, every star, every planet, every living world, and every one of us found the rare conditions needed to exist. Perhaps that is what makes our place in the cosmos so extraordinary. Not that the universe is full of life, but that life emerged at all in a universe so profoundly empty. If you enjoyed this deep journey into the universe, please subscribe to the channel so you don't miss our next feature-length space documentaries. And before you go, we'd love to hear from you. Leave a comment telling us where you're watching this documentary from. What country or city are you in? It's always inspiring to see people from all around the world connected by the same curiosity about the universe. Thank you for spending this incredible journey with us. Until our next exploration, keep looking up.